Now we come to definition of a very important term, material derivative. You will recall we were talking about Lagrangian way of defining kinematics or fluid flow, and this term is very much used when we are considering or adopting Lagrangian method for following fluid motion. So acceleration term is equal to, by definition, dv by dt. The total derivative is dv by dt, which is equal to, if we go into its components, partial derivative of v with respect to time plus the vector v times del into the vector v. Again, when we expand this, this will turn out to be u into du by dx plus to dv by dy and so on, and other terms that are related to this. So the first term, as we defined earlier, is the acceleration, and it depends upon time, and this is called as local acceleration. The other terms are known as advective terms or sometimes convective terms. So the total derivative operator d by dt in this equation is given a special name. So this term is given a special name, material derivative, and this is denoted normally in literature within the fluid dynamics by capital D by dt. Once we write capital D by capital T, we will interpret it as that this is being referred to the material derivative. And what is material derivative? When we are following each particles of a fluid flow. So each particle, where it is at time t plus dt, time t plus 2 dt, and so on. So this is just a representation just to show. Then other names that are given to this also is total derivative, particle derivative, Lagrangian, or even for other method, Eulerian, and substantial derivative as well. The material derivative d by dt is defined by following a particle, fluid particle, as it moves throughout the flow field. And in this illustration, the fluid particle is accelerating to right as it moves up and in the right direction. So the same thing is kind of being repeated. Acceleration is this. The essence of this point is that if we use the term material derivative, we will be referring to this term, and this is denoted by dv. In fact, if we are saying material derivative, then this will be capital D by capital T. And if we are talking about derivative of a particle or total derivative, then we, for acceleration, for calculating acceleration field, then this will be done by, for d by dt applied on velocity, and this will give us the acceleration vector that depends upon x, y, z, and if it is time dependent, that indeed on time as well. We shall be using this terminology whenever required and from case to case basis, or on the situation of the flow field that is under consideration.